A simplification of canonical equations of the forces method under the condition of symmetry of the mechanical system. This is article number just a moment, number 3.6. 3.6 from the book Mechanical Systems Calculations of the Marine Facilities. So to do the main issues of statics, to find the one of two main issues of statics. The first is the finding of the support sections, and second is developing of the balance equations. But for statically indefinable mechanical systems, when we have to use the concept of the system deformation and the conditions of the compatibility of deformations of the mechanical system statically indefinable, we can use the methods widely used. One of two is method of forces, another one is a method of displacements, but we are talking about the forces method. And we use the canonical equations of the forces method. For example, for the considered mechanical system on the figure 3.6.1, we have 5 times statically indefinable mechanical system here. If, for example, we will do the section cut of 2 parts, symmetric section in this system looks like geometrically symmetric. If we divide into 2 symmetric parts of the system, we can see that the cutoff part of the system for each another one part we have to substitute by the definite efforts. For example, the upper one rod, we have to substitute, when we cut it, we have to substitute for the left one part by the forces on behalf of the right one part. This is a longitudinal force action in the right cutoff part of the rod in the frame. This is a vertical part, transverse part for the rod. As well, this is a substitute of the absent unnecessary connection, unnecessary from the geometric point of view. And we have third effort is the bending moment. Bending moment action in the upper rod of the mechanical system of the frame. And this bending moment transmitted from right part to left, from left to right. But when we cut off 2 parts, we have to substitute the absence of the right part by the bending moment on behalf of the another part, for the right part, on behalf of left part, for the right part, on behalf of the right, for the left part, on behalf of the right part, etc. For the section, for the cut of the lower horizontal rod with a hinge here, when we cut just by the symmetry, geometric symmetry of the mechanical system. So we are talking about just only the geometric symmetry, and we assume that perhaps the rigidity equal on the left and right sides. We consider the mirror symmetry geometric of this mechanical system. We have to substitute by only 2 forces. One force is the longitudinal, another one transverse. So just do because the hinge do not transmit the bending moment. So we have together we have 5 unknown variables. And this is the main system, one of the options of the main system for the assigned system. Assigned system is 5 times statically indefinable. So we have 5 unknown variables: longitudinal force, transverse force, bending moment in one rod, in the continuous rod, and the hinged rod. We have only 2 forces, longitudinal and the transverse, due to the hinged rod do not transmit bending moment. The hinge do not transmit. So to find this all for the main system, we assume that each parts, the left one and the right one, geometrically symmetric parts, are statically definable. This is kind of the main system for the assigned system. Main system is a statically definable system. When we cut off in the force method, cut off the unnecessary links, unnecessary from the geometric point of view. That is, we assume that another part is not the cutoff part remains statically remains geometrically invariable. And so we assume that the cutoff parts are necessary just only from the point of view of the invariability, not from the technological or other points of view. We have to substitute the cutoff part by the action of the appropriate efforts in the cutoff part on the left one or for the right one from the left. So this is just for geometric symmetric. Actually, perhaps this mechanical system not for sure geometrically symmetric because we have to assume for the statically indefinable system not only the geometric symmetricity, because we have to assume the symmetricity of the external load. We have no external load symmetricity. Here we have the force, external load acting on the upper one rod of the frame. This force acts downward on the right part of the mechanical system. So it's not 100% mechanically symmetric. And to find the efforts in the absent part unnecessary from the geometric point of view to remain the rest part geometrically definable. To find these efforts, we have to use the extra equations of the compatibility of the deformations. The equations of the compatibility of deformations can be the equations of canonical equations of the forces method. So each equation, here we have 5 equations, if we have 5 variables for the main system. Each of the equations are, from the physical point of view, the displacement in the definite direction. For the first equation, in the displacement in the first direction, for the second, in the second direction, etc., up to 5 directions of the absent links. And the rule of the compatibility of deformations is that the displacements on behalf of all independent absent cut off the mechanical absent mechanical limbs we cut off to do the main system of the assigned system. All and together caused the definite displacement, like this is displacement on unit force. So guess when we do multiplication, we find the displacement under the force no unit, but any magnitude of force, etc. So and accounting as well the displacement in the first direction on behalf of the external load have to be equal to 0. This is a rule of the compatibility of deformations for 5 times statically indefinable mechanical system. As well, in the second direction, that the influence of all absent efforts and the external load together with the considered second one in the second direction have to be equal together to 0. This is compatibility rule for the decision of the statically indefinable system, etc. Until to the 5 efforts. 5 is a transverse effort in the law for the definite assigned mechanical system for the frame. So have to be equal to 0. The symmetry of the mechanical system for the statically definable is just only the geometric symmetry of the system itself and the external load applied for the statically definable. For statically indefinable, the symmetry means the same time the symmetry of the rigidity, so the elements of the segments of the mechanical system. Here we have assigned the same rigidity of the right one stay and the left one stay. So we have symmetric. We have geometrically symmetrical, and from the point of view of the rigidity, but only unsymmetric action of the external force. So the question arises: can we use, to simplify these 5 equations, can we use the property of symmetry of the assigned system, the geometric symmetry of the system, with just only absence of the symmetry of the external load? Can we use this symmetry property of the system? And for the system, we can, to simplify, we can use the symmetric main system, so statically definable system. For the assigned system, have to be symmetric to simplify the canonical equations for the finding of the absent for finding of the forces and efforts, maybe not the forces, maybe the moment in the cutoff segments of the mechanical system. Okay, so would consider please separately the bending moment diagrams action in the main system under the influence of the unit forces and the directions of the thought in the sort of the reactions in the absent links we cut off by use of we cut off doing the main system of the assigned system. So we cut off definite amount of the links in the assigned system, and we reduce the assigned system to the statically definable system, which would be the main, geometrically the same as the assigned system, with not the unnecessary links from the geometric point of view, to which not required to do the geometric interchangeability of the assigned system. Okay. For use of the canonical equations, next to find the unknown variables efforts in the cut-off connections in the assigned system to do mechanical system, we have to have the factors, the coefficient in the equations. The factors are the unit displacement and the action. This means displacement and the action of the unit force, or the force in the direction number 2 on the draft of 3.6.1b of the main system, and the action of each one definite force in the cutoff link when making the main system. Okay. To find these factors are the displacement in the considered direction and action of the unit force. We can use so-called Moore integral. Moore integral is a formula of the Moore integral is that to find the displacement for definite one, we can find the Moore integral, the total of the integrals. In the integrand is the fraction in the denominator of the product of the diagrams, product of diagrams of the diagram of the bending moments under assumed influence in the main system of the unit force in the direction of considered one displacement of when we do the corresponding the definite direction of the absent reaction when making the main system of the assigned system, and the second product in the nominator on the integrand of the Moore integral is the bending moment of the load under the load from which behalf we consider the displacement in the considered direction I. So for the canonical equations, we consider the displacement in each direction of the absent force and the influence of all others and the same one efforts. And so we have two diagrams. So we have one diagram of the bending moments in the main system and the action of the force in the considered one direction. This first for the first equation, first, etc. And the second index indicates that this is displacement and the action of the force in the direction for the considered one in each summand the force. Like it's 1, 1, 2, 2, 2, etc. This is F, it's under the external force F. And this is Moore integral, the kind of the determination, the approach to determine the displacement in the direction Y and the influence of the force or maybe moment in the direction K. So this in the nominator we have the product of these diagrams in the in the numerator. In the denominator we have the rigidity of the considered each one segment of the mechanical system. So and we can use to find the delta low case factor each one. We can use the diagrams of the bending moments of the main system and the action of the unit forces in the absent links when making the main system of the originally assigned system. And the property of this Moore integral is that when we find this integral in the numerator, the one diagram is symmetric, another one is skew-symmetric. The integral Moore gives us zero displacement. So only this have not to be the symmetric or skew-symmetric together. the product of skew symmetrics are definite magnitude of the displacement. The product of symmetrics in a numerator, two factors symmetric, two diagrams, gives us definite magnitude. But if one factor in the numerator is of the diagram of the symmetric action of the considered force, and the second one is skew symmetric, so the product gives us zero displacement. So, and besides, we have to assume the property of the reciprocity of the mechanical system. That is for each one the mechanical system, the displacement in each direction on behalf of the second one direction of force is equal the property in the second one direction in the influence of the first one direction of force. So this is a symmetry of reciprocity of the displacements of the mechanical system. So we assume that the property of symmetry acting on the Mohr integral that is in the numerator, these diagrams multiplied in the numerator have not to be together one symmetric, another one skew symmetric. It have to be or symmetric or skew symmetric only. Or but just without the property of symmetry, we can find definite displacement. If they are one symmetric, another one skew symmetric, the numerator of the Mohr integral, the displacement have to be equal to zero as a result of the use of the Mohr integral. And another one, the property we use, the property of the reciprocity of the displacement. So displacements in one direction, adjection of the force in another one direction equal to displacement in another one direction, the action of the force in the first one direction. So considering this set of the diagrams of the bending moments of the main system adjacent the each one of the each one of the unit force adjacent of unit forces in each one direction of the absent connection in the mechanical system. When doing that main system of the 5 times statically indefinable mechanical system, we have five diagrams. The first one is symmetric. Symmetric relatively this axis. Second one is skew symmetric. So the displacement in the direction of one force absent, subject to find under the displacement of under the action of the force as well, subject to find. And the second direction, each is symmetrically equals to zero. So the displacement in the first direction and the action of the force of the second direction, and the displacement in the second direction and the action of the force in the first direction is equal to zero. Is equals in between and equal to zero finally. So, and we'll please consider all this set of diagrams which are in the Mohr integral, which cause the products of the diagram symmetric by the skew symmetric. So this is the first and the fifth. Yes, the first symmetric, the fifth is fifth diagram skew symmetric. So this this factor and the displacement and the action of the unit force in the fifth direction in the displacement in the first direction equal to zero, and the displacement of the in the fifth direction and the action of the force applied in the first direction unit force equal to zero too. So second diagram skew symmetric, and so the third diagram is symmetric. So the product of diagrams, product I mean the application of the Mohr integral to find the displacement. The product actually only is in the numerator, in the integrand, in the total of the Mohr integral formula. Yes, it is, but to say a little bit brief, we can say that it is a product of diagrams. Product of diagrams, I assume that this is a use of the Mohr integral to find the displacement. With insight to use the diagram products, yes, but it is only as well the mathematic transforms of integration and the transform or total of these integrands, integral functions of the integrands. So the second diagram, skew symmetric, the force symmetric. So product have to be equal to 0. The force skew symmetric diagram, and the second, this is reciprocity of the displacement, have to be equal to 0 together. The displacement in the third direction, that is symmetric conjunction of the force applied in the second direction, in the fifth direction, sorry, and as well the symmetric the displacement in the fifth direction and direction of the force in the applied in the third direction have to be equal to 0. And the force diagram symmetric, fifth not symmetric, so the displacement and action of the unit force in this one direction and the influence of the unit force applied in the another one direction, as well as symmetrically the displacement and the action of unit force in the fifth direction and the action of force applied in the fourth direction have to be equal to 0. So this all make us possible to simplify the originally had system of the canonical equations of the force method using the property of the symmetry. We have only three we have two, actually, first of all, we have just mathematically independent two systems. So we can find the symmetric x1, x3, and x4, the forces by one mathematical system of the equations of the canonical equations of the force method. And we have another one, two equations in the system to find the force action skew symmetrical. So this is a simplification of original canonical equations, so the force method using the property of symmetricity, of geometric symmetricity of the assigned mechanical system using the geometrically symmetrical main system. To have geometric symmetricity of the main system, we have to cut this main system into two parts by the line of the symmetry. So we have, this is the use of the symmetric statically definable main system. Yes, okay, so we can simplify it by this way the canonical equations. Another one approach, let's assume the independent terms of canonical equations that is this one, independent and the free summands of the canonical equations, the displacement in each direction and direction of the external force. And let's assume the available options. If, for example, the external load is symmetric, like here, or this is skew symmetric. First of all, I would like to underline that it can be as well the application of the external force due to the axis of symmetry. Yes, a force, for example, here. Longitudinal force along the axis of symmetry we assume as symmetric. If we have the force applied transverse to any of elements of the mechanical system, symmetric mechanical system, if we have the transverse force applied to the element on the axis of symmetry, it is, we assume, like a external load skew symmetric, transverse, longitudinal symmetric to the any of the elements of mechanical system which would be on the axis of the symmetry. Okay, so we can as well consider that when we assume, for example, the left one part of the originally had canonical equations of the force method simplified, where we exclude the summands here of the first three. First three is the one, excuse me, this no first three, this is after mathematical transform of the assigned mathematical equations. Like here we have the mathematical equations just very formal, appropriate for this just mechanical system. After that we simplify that and have three mathematical equations for the symmetrically applied application, symmetric application of the forces on behalf of the cutoff part of the mechanical system assigned making the main system. And we have the final, the free terms. Free terms is independent on the variables under consideration, the variables x1, x3, x2. This is forces applied symmetrically. This is x2 and x5, the efforts applied to the mechanical system, main mechanical system, asymmetrically. And we have the free summands in the equations here and here in each cases. And these free summands as well we can find by use of the Mohr integral as well, by the product of the diagrams of the bending moments injection of the unit force in the considered one direction of the absent link when doing the main system of the mechanical system, and the second the bending moment injection of the external load, the bending moment. And we have in the options of symmetrical application of the external load, we have the diagram of the bending moment like indicated on the figure 3.3, 6.3 on the left, and injection of the skew symmetric external load, we have the diagram 3.6.3b. And when we substitute the diagrams into the Mohr integral to find the displacement, and in the each one consider direction of the cutoff links and direction of the external force, and the forces in the cutoff links could be symmetric or skew symmetric, in the use of symmetricity of the geometric symmetricity of the assigned mechanical system, and the way of the use is the doing of the mechanical doing of the geometrically symmetric main system. So after the substitute these diagrams into the Mohr equation here, the diagrams of the bending moments injection of the external force, like here, symmetric or skew symmetric, and the diagrams of the moments injection of the unit force in the forces section of unknown variable in the canonical equations. So we can find that the free summands have to be equal to 0 if we can assume the this is after the simplification using the skew symmetricity of the for skew symmetric application of if the absent link are skew symmetric, so this would be equal to 0, this free summands in these equations, if the external load would be symmetric. So for the first case of the application of the external load and the exertion of these forces, the factors, the free summands in the mathematical equations would be zeros. If we are looking for the forces applied on the main system after the cut of the necessary links, if these forces are skew symmetric, but if these forces external load would be symmetric. But if the applied external force would be skew symmetric, so the free summands will be equal to 0 for the equations, canonical equations of the forces method. If the unknown variables here is the magnitudes of the efforts instead of the cutoff links skew symmetric. Yes, I'm sorry, symmetric. So if the force is symmetric and the variables are symmetric, the force is acting symmetrically in the mechanical system when we're doing the main system of the assigned system. So this will have the definite magnitude if all and efforts and the forces in the cutoff links are symmetric. But if this external force would be skew symmetric, but the action of the force is subject to determine here in the equations is skew symmetric, but the forces are symmetric, so this will be equal to 0. And what mean the equality to 0 of the free summand in the mathematical equation? This means the equality to 0 of the forces. Because when we have no the free summands in the mathematical equations, only zeros and only the summands with the products of the unknown variables for definite one factors, this will go to 0. We will have 0 magnitudes of the forces if under action of the symmetric external load, we will have 0 magnitudes of the forces in the cutoff links, in the skew-symmetrically cutoff links. If we have skew-symmetric application of the external load, we will have 0 forces in the symmetric cutoff links. So if we have 0 skew-symmetric external forces, like on the figure 3.6.3 b, we will have zeros forces which are applied symmetrically, but external load skew-symmetric. So they will be 0. This follows from the canonical equation due to the application, due to the rules of the finding of the factors and free summands with more integral by the product of the diagrams, and the symmetricity or skew-symmetricity acts that the products will be 0 if one factor in the numerator of the integrand of the more integral one of factors will be, one of factor is a diagram of will be skew-symmetric, another one symmetric. So they have to be or symmetric or skew-symmetric at the same time. And this is the second approach to reduce the number of the variables in the canonical equations. If we beforehand can know that a part of the variables will be equal to 0, considering the symmetricity of the application of the external load or skew-symmetricity, and considering the symmetricity or skew-symmetricity of the application of the loads in the cutoff links when doing the symmetric main system, statically definable of the statically definable assigned mechanical system. And the another one usable approach for grouping unknowns when calculating statically definable symmetric system. If, for example, we have the system like indicated on the figure 3.6.4a, this mechanical system is 4 times statically indefinable. So, and we have to have find by the canonical equations of 4 variables. Like here we indicate on the main system geometrically symmetric main system, which we do from the assigned system, which we did from the assigned system A. On the figure 3.6.4 b, we have geometrically symmetric main system, and it is not 100% symmetric because the force applied not symmetric here. Although we assume that the rigidities of all elements of the mechanical system are equal to each other, and it looks symmetric, but it's not symmetric as the point of the application of the external force shifted to the right. So does this mean that the efforts we apply instead of the cutoff links when doing the main system of the statically indefinable mechanical system, the magnitudes of the efforts, x1 transverse force, x1 stroke, x2 strokes longitudinal force, x4 stroke longitudinal force, from the support reaction absent when doing the statically definable main system of the assigned mechanical system, and x3 stroke as well. They all are, these efforts are of the other magnitudes. They are not symmetricity. There is not symmetricity of the magnitudes of the forces applied instead of the cutoff links, due to asymmetricity of the application of the external force. But we can do the variables substitute. For example, in what way we can consider the substitute of the variables? Let's consider the force x1 stroke, x the total of two assumed forces, x1 and x3. And let's assume that x2 force here is not just a force x2 stroke, but a total of two forces, x2 and x4. And on the right support, let's assume that x3 force, transverse force applied here to the end of the frame on the right. x3 force equal not the total, but the subtract with x3 of x1. And x4 force, this one, longitudinal force, in the support, let's assume equal to the subtract. x4 is assumed with that we have another one variable, x4 of x2. After the definite mathematical transform, we can find the set of the equations that x1 equal to half total of x1 stroke and then x3 stroke. x2 is half total of x2 stroke and x4 stroke. x3 is half difference of x1 stroke and x3 stroke, and x4 is half difference of x2 stroke and x4 stroke. Okay, so we indicate this all forces x1, x2, x3, x4 here on the action on the ends when cut off the links of the assigned system instead to do from the assigned statically definable 4-time system when doing the statically definable main system. And this is the indication how we apply these forces. Forces instead of the assigned originally on behalf of the links absent when we cut off doing the main system. And what are the diagrams of the action of unit forces indicated x1, x2, x3, x4 indicated on the figure 3.6.4c. The diagrams we see on the figure 3.6.5. So this is a diagram of the external forces action on the of the symmetric diagram of bending moment and action of the unit force applied in the force direction. This is symmetric diagrams of the bending moments and action of the unit force x2. This first one was from x1. C is skew-symmetric diagram of action of forces x3 action on the main system. This is skew-symmetric diagram of the bending moments as x3 applied skew-symmetric. And this is a skew-symmetric diagram of action of the forces x4 instead of the absent cut off unnecessary connections in the assigned system when making the main system. The diagram of the IX4 after the redefinition of the unknown variables instead of the x1, x2, x3, x4 with the strokes, we substitute by the definite mathematical transform with x1, x2, x3, x4, etc. And we have the diagram on behalf of action of external force. So considering the indicated diagrams after the substitute of the variables with strokes to another one variables with no strokes using the property of the symmetry and skew symmetry, we can find that for the originally we assume that we would have originally when we consider the 4 times statically indefinable system to decide the system by the forces method. Actually in the general approach, we have to have the canonical equations, 4-equation system of the canonic equations or the forces method. But we can reduce this to 2 systems of 2 equations each to find the magnitudes of the assumed the forces x1, x2, etc., and x3 and x4. We will consider this each 2 the couple of the canonical equations of the forces method separately as some factors using these variables x1, x2 did by the mathematical linear transformers indicated here on the slide. We considered considering the symmetricity and the skew symmetricity of the bending moments diagrams and the action of the unit forces x1, x2, x3, x4 with not strokes, some of them are equal to 0 if we consider the displacement in the direction of the of any symmetrically applied force, for example x1. And in this direction we would like, if we will find the displacement and action of the skew-symmetric application of force. So skew-symmetric application due to the property of the Mohr integral, if we use Mohr integral to find the displacement or injection of each one force in the direction of any other force, or so we will have the 0 displacement if one diagram will be symmetric, another one skew-symmetric. So a definite set of the displacements, which at the same time are factors in the canonical equations of the forces method, the displacement injection of the unit forces, we assume that these forces if equal to 0. And after that, we can decide very easy the mathematical equations, only 2 equations with 2 variables and another one system of 2 equations other with 2 systems as well. And we will then consider the just arbitrary application of the force, which is not symmetric or skew-symmetric. So we assume that each free summons in the equations will not be equal to 0. So force is not. If, for example, the force would be symmetric, for example, we would have another one force applied here on the left as the same as this one assigned on the right. So in this case, if it will be the canonical equations will be zeros. So free summons will be 0 and the efforts will be 0 for each applied skew-symmetric forces on behalf of the cutoff reactions when doing the main system of the assigned system. So having this independent unknowns found, one can determine the reactions of the supports. That after that, when we have already got x1, x2, x3, and x4, we can find next using these equations on the last line of the slide when we did the mathematics transform. We can find the originally subject to find the forces x1, x2, x3 with the strokes, which were originally for the assigned which were originally for the main system statically definable, appropriate to assign them system statically indefinable. Okay. Questions and comments. 3.6.1 the symmetry qualities of statically indefinable mechanical system. Statically indefinable mechanical system could be geometrically symmetric, and the symmetry assumes not only the symmetry of the mechanical part of the system, but as well the symmetry of the external load and supporting reactions symmetry as well, and the symmetry of, for statically indefinable system, the symmetry of the rigidities for statically indefinable system, of symmetry of rigidities. We can have a symmetry or skew symmetry for the mechanical system, and we can use this to simplify the canonical equations of the forces method. simplifying the calculation of statically indefinable system by choosing a symmetric main system. We can reduce the number of equations if we consider the symmetricity. So as for the symmetric mechanical system, when we do the symmetric main system statically definable, which in other case appropriates the assigned systems. Assigned is statically indefinable. That's why we have to use the canonical equations of the forces method. And first of all, to do these equations, we have to decide what is the main system. For a symmetric system, could be more fruitful to use the statically definable main system symmetric 2. Mirror symmetric, skew-symmetric diagrams of moments in the elements of main system formed for a given symmetric statically indefinable mechanical system. The absent unnecessary links we substitute by the forces. The forces action could be symmetric or skew-symmetric. And in the canonical equations, we consider the displacement and action of the unit forces in each direction and the action of the forces in all others direction. And the properties of symmetric and skew-symmetric diagrams useful is that the displacement in the directions of the symmetric unit forces equal to 0 under the action of the unit forces applied skew-symmetric. The same as we consider the reciprocity of the displacement, the property of the proportional elastic systems, reciprocity of the displacement, the displacement in the directions of loads action skew-symmetric, and the action of the mechanical system of forces applied symmetric would be equal to 0 too. This attributes to the products in the Mohr integral of the diagrams of the unit forces, and as well when we find the displacements and the action of the external load, that is for the canonical equation, the free, so independent on variables, on variable unknown forces and the absent links. This is so the summons, free summons, which is for the canonical equations of the forces method, which are the displacements and actions of the external load. We call it T2 Mohr integral values of the product of moment diagrams, one of which symmetric and the second one is skew-symmetric. Yeah, we use this to find the property of equality to 0 of the Mohr integral values. We use this to find the factors of the canonical equations, which is the displacement and action of the unit forces, equality to 0. And equality to 0 the free summons, as well as the diagrams in the numerator of the integrand of the Mohr integral as a product of the two diagrams of dependent moments. If we are considered dependent, could be not only dependent for other kinds of the mechanical systems, could be the diagrams of the longitudinal forces, or maybe the shearing forces. So we consider the shear deformation or longitudinal deformation. But in this different one case, when we consider the bending of the mechanical system, the zero magnitude of Mohr integral, the zero result of the determination, satisfies the product of diagrams, which one is of the property of symmetry, another one of the property of the skew-symmetry. So in the more general approach, we can say that the approach to reduce the complexity of the canonical equation for its decision using the symmetricity is that use not only symmetricity, but it is use of two properties of mirror symmetricity and skew symmetricity. And if we consider this together, this acts on the mechanical system like a separate. So forces with the property of symmetricity and skew symmetricity on the mechanical system as a separate forces. This we can attribute not only to the external forces, but as well to the considered forces of the cutoff links when doing the main system statically definable or the statically indefinable assigned system. 3.6.5, the simplification of canonical equations of the forces method, in which the system splits into two systems of equations containing unknowns, which diagrams of moments are either only mirror symmetric and skew symmetric. Yeah, this is just the way to reduce complexity of canonical equations to decide these equations. Due to the after the exclusion of some summands of the equations which corresponds to the displacements or in the mirror symmetric directions under action of the law of the skew symmetric nature, or the displacement in skew symmetric directions under the influence of law of the mirror symmetric. This summands and the factors in the canonical equations of the forces method will be equal to 0. This reduces the number of summands in the canonical equations and usually make it possible to, instead of one system of the equations of the canonical equations, allows to decide two independent systems of the canonical equations. 3.6.6, equality to 0 of displacements of a symmetric external load, the three terms of canonical equations of the forces method. In equations with unknowns having skew symmetric diagrams want equality to 0 of these unknowns themselves. So the same property of symmetry of skew symmetry. Skew symmetry I usually understand as a mirror symmetry. The property of the application of symmetric, mirror symmetric, or skew symmetric application of the external force as well, you can use to reduce the number of the equations. If we consider the direction of the displacement of the any effort in the main system, which is of the symmetric nature, and the external force would be skew symmetric, the displacement will be in this definite one direction of the force will be equal to 0. The direction is displacement of the unknown force subject to find. If it is symmetric and the force applied is skew symmetric as well, if the force we look for unknown variable of the canonical equation applied skew symmetric and the force external applied symmetric, so this force subject to find will be equal to 0 as well. So sometimes we can consider the symmetricity or skew symmetricity of the external load and symmetricity of or skew symmetricity of the forces in the support reactions or other links when doing the main system of the statically definable main system of the statically indefinable system assigned. Sometimes we can decide about the magnitude of the efforts in the cutoff links beforehand with no decision of the canonical equations if we just assume the symmetric or skew symmetric property of the unknown variable we look for, and symmetricity or skew symmetricity of the external load. So thank you.